to see how low the lake had gone. Just even in the 4 months since the ferry ceased operation, you see Lake Powell out there in the distance, my car for scale. It was just, frankly, it was shocking to see this. I took this early in the morning. And here's the second photo I took from that exact same ferry ramp, only at the top. The arrow indicates the end of ramp. You can see in the inset the same photo as before. If you're a student of Southwest geography, that's Navajo Mountain off there in the distance, which is visible from large portions of the American Southwest and often serves as an anchor to show you where you are. The lake's down another 30 feet even from here. And as I understand it right now, I don't think a single marina is in operation on Lake Powell right now. Or there may be one ramp actually that's operable, but it was stunning to see it. And this whole topic, this whole talk deals kind of with how we got where we are today. So this image is the combined Lake Mead and Lake Powell volume from 1935 when Mead was first made operational. And then in the 1970s, Powell came online, and that's the big ramp that goes up in the middle of this image here. On the left is volume in millions of acre feet. And I assume you all know what an acre foot is, right? 325,000 gallons, kind of the standard measure we use in the American West. And on the right is percent full. And also off on the far right here are some projections out of what Reclamation calls their 24-month study, both in the blue and red dots. And you can see we're headed to about 27, actually in the minimum probable, maybe even 15% full by something like 2024, mid-2024, those dotted lines go out to. So what's happened here? So in January of 2000, the two reservoirs were 95% full, 47 million acre feet, 3 times the annual flow in the 20th century of the river of about 15 million acre feet. By April 2022, this year, less than 30% full, 15 million acre feet. And that's a loss of 32 million acre feet, or about 1.4 million acre feet per year. It's 2 times the annual flow again of the river. How'd we get here? That's sort of the story of this talk. And I want to make a point here on this. We did not have, in this period since 2000, one 2-year period where these reservoirs filled. That little blue circle here, that's 1 year. That's 2011. That's a really big runoff year on the order of 20 million acre feet. But you cannot find 2-year consecutive years here where it fills. It either goes down or it stays flat. And that's sort of astounding compared to what happened in the historical record. So I could spend a whole talk on just this map. A little background, I think most of you probably know. I mean, how many of you think you know it? Give me a show of hands. You know all this stuff that I've got listed here, kind of basic stats, kind of, maybe, sort of. All right, let me go through it quickly. So 7 different states in the basin, right? 2 nations, 30 tribes. We used to think 29. We now know there's 30. It's really importantly, it's divided. You can see kind of in the middle of this, upper and lower basin, in a place called Lee's Ferry. And a little family history here. John D. Lee founded that ferry. He was sent there by Brigham Young to kind of get him out of the way because of a really sordid tale in Utah history called the Mountain Meadows Massacre. Turns out Udalls are actually Lees. My sister's name is Catherine Lee Udall, and that goes back to John D. Lee. I'm Lee's great-great-grandson. And the funny thing here is you might think this is kind of unique, but Lee actually had, we think, 21 wives. And so he may have as many as 800,000 descendants right now. And it's not all that hard to be a great-great-grandson or great-great-granddaughter of John D. Lee. But Lee Ferry is a really important part in the area of the basin. The annual flow now, if you average, including the 21st century years, is 14.75 million acre feet, down from a little over 15 if you just do the 20th century average. The worst drought in the gauged record. And actually, you know, I made it, so many people do this, it's worth pointing out. How many of you know about the natural flows? When I say natural flows, so we reconstruct at Lee's Ferry and in other places in the basin, what we call natural flows. What would happen if humans were not there? And these are really important for scientific research. We have to add all the diversions back in and lake evaporation, everything that humans do, we add it back in. We create this synthetic record. And here I've referred to as a gauge record, which everybody does, but it's not really a gauged record. Yeah, we have a make-believe gauge at Lee's Ferry that we think would be accurate if humans weren't around. But I just want to point out that those natural flows are synthetic, and there's some issues with them, but they're really important. And here I tell you that they've declined about 20% in the 21st century. And that's behind, along with mostly lower basin overuse of water, that huge decline in that first image of the combined contents. Yeah. Yes.
What is the variable that would cause that to be?
So the really big wild card there is how much water crops consumptively use on a field. And those flows use something called Blaney-Criddle, which, if you know a little bit about how crops use water and the different methods, this is an older method, it's not that accurate. And there's a whole process right now, a whole effort called OpenET, that's an effort to try and get really good consumptive use numbers on flows. And at some point in time, we will make new natural flows at Lee's Ferry, and they're going to look really different than these ones we've been using for a long, long time, and cause a lot of people a lot of consternation. I think that they'll be highly correlated, but the numbers themselves will be different.
If you wouldn't mind, if you get a question from the class, if you could repeat it.
Yeah. Okay.
Can you repeat the questions, please?
The question was,
What variable is kind of like I guess other variations considering this entire natural?
what are some of the problems with the natural flows in particular? So what big variables are there? Yeah. So yeah, I stand whatever, corrected. So all these big arrows here are diversions out of the basin. And I mean, it's amazing how many really big diversions there are. And oddly, more water gets used out of the basin than in the basin. I mean, you could make an arguable claim to that. Half the water here in Colorado's Front Range is Colorado River water. Albuquerque now is highly reliant on Colorado River water through something called the San Juan Chama project. Salt Lake gets Colorado River water. It goes into Los Angeles and San Diego, and it's about 25% of their supply. It's 90% of the supply in Las Vegas, arguably in the basin there. It gets pumped uphill, about 10% of it gets pumped uphill into Phoenix and Tucson via something called the Central Arizona Project that I'll talk about later, because it's really a critical part of the issues we're now seeing. It was allocated famously in 1922 by the Colorado River Compact that I'll talk about. Around 2000, we think withdrawals and supplies were for the first time were equal. People still want to build new projects. It rarely makes it to the ocean anymore. Shockingly, we take every last drop. And then finally, and I'm going to talk about this too, in June of this year, the federal government announced that we needed 2 to 4 million acre feet in reductions for 2023 and years beyond to make sure the system's reliable and stable. And that's a stunning admission by the federal government. And it's additive to plans that were made in both 2007 and 2019 to cut back deliveries as the reservoirs decline. But the total amount of those cutbacks are on the order of about 8 or 9% anticipated by 2007 and the 2019 agreements. This is more like twice that, 15 or 16% to 30%, depending on whether or not you pick 2 million acre feet or 4 million acre feet. And this, frankly, right now has thrown the whole basin into a bunch of uncertainty, and there's no clear path how to get those reductions, I would argue, right now, unfortunately. So a year ago, in August of 2021, the way the river gets managed is the reclamation, the river manager, is what's called the 24-month study. And in that are some reservoir elevations. And based on those projected reservoir elevations, we then determine what kind of year it's going to be. So for the first time in 2021, we hit what's called a tier 1 delivery shortage. And this made news everywhere. The Economist, upper right corner, CNN, lower right corner, Washington Post, Circle of Blue. It was a really big deal. And these reductions are on the order of just roughly, I would say, 3% or 4% of total water use. And those reductions are to the lower basin. You know, one of the things that's super interesting about this basin is the upper basin and the lower basin operate very differently. The lower basin gets the benefit of those two really big reservoirs, and they're completely met, their demands are met by reservoir deliveries. The upper basin, not so much. I mean, there are reservoirs in the upper basin, but a lot of the diversions that go on are run of the river kind of diversions, where if there's water in the river, you can take it, and if there isn't, there isn't. You don't get it. There's no reservoir to deliver your water. So I want to run you through a few news clips just from this year to show you how things have changed. So here's May 3rd on this year. As drought crisis deepens, government will release less water from Colorado River Reservoir. And basically what they said here was that they were going to actually reduce the planned release from Lake Powell and keep that water in Lake Powell to try and keep it above some levels that would actually promise that they could generate hydropower. Because all of a sudden, and this isn't in the compact, in fact, it's a secondary purpose in the compact, power generation, all of a sudden it looks like power is something really important. And that was something that most water users in the basin wouldn't have counted as much on. And so this was a really big deal. Here's almost a month, 6 weeks later, as water crisis worsens on Colorado River, an urgent call for Western states to act now. So this was the announcement made by the Commissioner of Reclamation during her testimony in front of the US Congress that we needed to find this water, these 2 to 4 million acre feet in cuts. And that they gave a demand that people come up with this within 60 days or the federal government would impose these cuts. Here's a story in July 15th, so about a month later, that's just about all the science that's gone on over the years. And Colorado River science, as you might imagine, I mean, it goes back decades. A well-known scientist named Peter Glick in the 1990s wrote one of the first studies on how climate change might impact the river. In the early 2000s, there were a number of studies. And then if you flash forward to about 2010 and later, there have been a lot of studies on how the river might be affected by warming temperatures, including some that I wrote. In fact, there's a famous study around 2010 that suggested Lake Mead could dry up by 2020. That was in 2010. And it was based on a couple of things. It was based on large use in the lower basin and potentially declining flows through time. And oddly, that study was really panned by decision makers. It was not well liked. But you know what? It turns out that study is probably more prescient than anybody would like to admit. So anyway, this article here, I'm not going to talk a whole lot about the tribes, but they were excluded from the original negotiations in 1922. There are 30 of them. They hold these very interesting water rights called winters rights that are federal reserved water rights. They don't go away if you don't use them, unlike most water rights. And they're really important because they're highly senior within the system. And the tribes recently have been upset because they now control about 20% of the water, but there are a whole series of tribes, I want to say about 12 out of the 30 that don't have quantified water rights, still 100 years after the compact. And they're really kind of getting their elbows out and saying, we deserve some equity here. As you might imagine, in a declining system, trying to figure out how to meet these needs is yet one more challenge. So here's August 17th. So another 24-month study comes out in August, right? I talked about the one in 2021. This is the one in 2022. And guess what? The reservoirs now are not below elevation 1075, but below elevation 1050 in Meade, which means a tier 2 shortage would be imposed, meaning yet larger declines, especially for Arizona, because of a very interesting artifact of how the Central Arizona Project was approved by Congress way back in 1968. And here's the story, and this is a little more Udall family history, actually, because it's sort of, well, it's interesting and scary. In 1960, Arizona had long wanted this Central Arizona Project, this huge canal that moves 10% of the river into Phoenix, which has one surface water supply, and all the way into Tucson, which has no surface water supply. A lot of groundwater, but no surface water supply. Arizona had long wanted this. It took a Supreme Court ruling in 1964 to give Arizona kind of the rights it needed and to remove some uncertainty versus California as to who owned what portion of the river. And in 1968, the Congress finally agreed to build this project for Arizona. But the price imposed by the state of California was that should there ever not be enough water in the river, the Central Arizona Project would go dry before California had one drop of shortage. That's what it took to get this through the U.S. House of Representatives. And the reason I mention it personally is my father was one of 3 Arizona congressmen that shepherded this law through the U.S. House at the time. And it's sort of odd for me to be working on the issue, some 50 odd years later. And this particular agreement right now is really, it's problematic. Because I have maintained for some years, you cannot dry up the Central Arizona Project Canal. You just can't do it. You can cut it back, but there are too many entities that are dependent on it, Native Americans, municipalities in particular. And yet California still wants to hang on to this 1968 promise that they thought that we would dry up this major canal. And here you kind of get sort of where we are in the lower basin. These are recent statements within the last month. Here's from a really important decision maker in Nevada. Yet, despite the obvious urgency of the situation, the last 62 days, going back to June, produced exactly nothing in terms of meaningful collective action to help forestall the looming crisis. Or here's Arizona. It is unacceptable for Arizona to carry a disproportionate burden of reductions for the benefit of others who have not contributed. Others means California here. And here's Southern California. Even though the basin states have not yet agreed on a consensus-based solution to address these declining reservoir elevations, California will continue implementing additional conservation programs in 2023 that result in meaningful water contributions to the system. Most people interpret that to mean we're just going to continue on as we have before. Hence the sort of issue we have right now, where these reservoirs are headed downward and nobody wants to see them a dead pool where you can't actually take water out of them. And yet nobody seems to really want to step up here and help solve the problem. Okay, so that's sort of an introduction. Let me do some science here and talk about how every trend we got in the scientific realms in the wrong direction here, unfortunately. I want to explain how pretty good snowpack here, like 85%, can turn into 30% of runoff. I want to quickly go through about 10 scientific studies just to sort of paint a big overall picture of the West and where we're headed because of climate change. I want to tell you that this really isn't a drought. People continue to call it a drought. It's not. I really object when people call this a new normal. Why? Because it's not normal. Normal implies predictability. Normal implies you can kind of adapt to it. It's not. If you want to call it something, call it the new abnormal. If you want to be cutesy, but please don't call it the new normal. What it is a mouthful. It's aridification. That's the term that a lot of scientists have picked up on. And that's the long-term warming and drying that we're seeing. Not every year is warmer, not every year is drier, but that's our trend. I want to talk about some worrisome projections, and then I want to talk what should we plan for. And let me just quickly walk you through that image here because it's got every trend I'm going to talk about, or most of them. The upper one you've seen, that's the combined contents of Powell and Meade. The panel B there is upper basin natural flows. On the left is millions of acre feet. The jaggedy lines are the annual flow. There's a horizontal average. There's a blue thing that's like a moving average. And then there's some red linear trends. And it's pretty clear those upper basin natural flows are headed downward, right? And I already told you, we had a little discussion about the upper basin natural flows at Lee's Ferry. Upper basin precip, same kind of graph, except for now we have inches on the scale. And again, you can see in recent years, this downward trend that's really worrisome. And since 2018, I'll show you just how worrisome that's been. Much of the science, actually until 2016 on the river flow reductions, was based on what's the warming doing to flows. We knew precipitation was down a little bit, but it didn't seem all that bad. And then all of a sudden we had 2018, which is awful, the single worst year since 1895, 2019 pretty good, and then the other years not great. I'll talk about that. And then the final one's upper basin temperatures, which shouldn't surprise anybody in this room. And I'll have more on each one of these as we move forward. All right, so just a quick map. So Moab's in the upper right corner. I'm going to show you in a little bit an image of Height, which is one of the old marinas of Lake Powell, just below Canyonlands National Park. I showed you an image at Bullfrog. And then Page, Arizona, where the dam is, Glen Canyon Dam is, has two marinas, one called Waweep and one called Antelope Point. I'm going to show you some photos of those as we go along. So here's Height. I took the photo on the right on that trip down to Page in October. And it's from an overlook. That's a paved overlook. And there's the river. It's heading sort of north off into Canyonlands National Park. If you look carefully on the left, you can see Utah Highway 95. When I got home, somebody pointed out to me that there was a stock photo from the year 2000 from that same spot. And if you don't believe me, it's the same spot. In the foreground, there's a rock that's really obvious, especially on the left image there. Same exact spot. Lake's full on the left and about 30% full on the right. Unbelievable. So also, if you pan the camera here to the right, you can look at the old Height boat ramp. You can see it there on the left image. Looks like a landing strip out there in the distance. And if you go down to the end of the Height boat ramp, you get what's on the right there. I mean, the river's still there to be seen, right? It's incised in this little canyon now. And the joke amongst the boatmen in Cataract Canyon and elsewhere is that the river is now cutting through what they call the Domini Formation. Wade Domini being the commissioner of reclamation when Glen Canyon Dam was built. And it's really muddy and kind of yucky and sort of awful, actually, if you're a river runner to deal with. Anyway. All right, so let's look at Lee Ferry natural flow declines. I told you they were 20% down, right? Bar chart, 1 bar per year, flow in millions of acre feet. And how are the last 22 years different from the 20th century? The natural flows go back to 1906. So the mean for the 20th century, 15.2 million acre feet. You can see it there in red. And the mean since the year 2000, 12.3, that's the 19% decline. I spoke about that earlier. High flow years, so years greater than 15 million acre feet, we have half as many. And those are the years that we fill our reservoirs. And in a couple slides, I'll show you matching precipitation that shows just how few really high precipitation years we've had. Low flow years, less than 10 million acre feet, we're getting 2.5 times as many as those. And if you took the worst 22-year period in the 20th century, if only that had repeated since the year 2000, our reservoirs would be twice as full as they are right now. They'd have 55% of their capacity, not 27%, to give you an idea just how different the flows have been since the year 2000. And they're the two numbers that the worst 20-year period or 22-year period. There's no analog between now and what happened in the 20th century. That's your take-home message. All right, so we also look at what are called the unregulated inflows in Nepal. God, I'd love to get rid of that thing there, but I guess I can't. So these are the unregulated inflows. These are the flows that would happen in Nepal with the effects of upstream reservoir operations removed. They actually have depletions or upper basin diversions embedded within them. So they don't have kind of the funniness of the demands in the upper basin in them. And they tell a good story too. If you took these flows and added the demands back in, you'd have something like the natural flows. So the average over the last 22 years is 8.4 million acre feet. So what's so bad about that? So the Colorado River Compact, Article 3 is the money part of the compact, and it allocates the river between the upper basin and the lower basin. And Article 3 says that the upper basin shall not cause the flows to decline below 75 million acre feet every 10 running years. After the compact was passed or negotiated in 1922, a Mexico treaty came about, and we now interpret that 75 million acre feet to mean 82.3 million acre feet, because the upper basin at least nominally has an obligation to Mexico as well. And so that 10-year running number is 82.3 million acre feet over 10 years. So let's do 1/10 of that, 8.23 and 8.4. Those two numbers are pretty close, right? Well, you can't just release from PAL what flows in, the 8.4, you got to subtract evaporation out. So what we've seen in the PAL that we can release since 2000 is about 7.9. That's less than 8.23, right? That's less than what we commonly accept as the upper basin obligation to the lower base, to the lower basin. That's highly controversial what that number really is. And I would argue, and this is an important point, in 1922, the upper basin agreed to that number, thinking that there would be droughts of certain periods, but that the mean flow of the Colorado River would stay the same. And what they were taking on was drought risk, not climate change risk, of a permanent reduction in flow. And so this is another outstanding issue right now within the entire basin, is who bears the brunt? Who should bear the responsibility for these flow reductions? Go back into the 20th century, many scholars and others thought, oh, that's a hard and fast obligation, that 82.3 million acre feet every 10 running years. I would argue it's not, that's not what the upper basin agreed to it at all. In a stable, stationary climate, yes. In a climate that goes down, that's not what the upper basin agreed to. And so that's my take home here. There's not enough water coming into the upper basin, into Lake Powell, to meet the deliveries that the lower basin has come to depend upon. And the reason we've met those deliveries since the year 2000 is we've drawn down Lake Powell to make it. That's what's happened. All right, what about precipitation? So this is just a blow up of that image I talked about earlier. Annual data is the really jagged in gray, inches of precip on the left. There's an average line and the linear trends, and then the blue kind of moving average. So since 2000, this is the worst 22-year running average, going all the way back actually to 1895 for precipitation. And the lows are record-setting and numerous. So 2018 is the worst year all the way back to 1895. There's 2020, another bottom 10 year, 2021, a bottom 20 year, 2012, bottom 10, 2002, bottom 10, 2000, bottom 20. So a third of those years are in the bottom 20, a third of them. And you can see again, after about 2018, at the lowest line there, we've had a series of really bad years. And also, and I hinted at this earlier, we're not seeing these high precipitation years either, right? I told you we're half as many big flow years in the river. There's only 3 really big high flow years. There's a number of other smaller ones above the average. But if you first off, look at the lower blue box and move that visually just off to the left. I dare you to find another period like that in the history that I'm showing you here. And conversely, look at the upper blue box and move it off to the left. It doesn't really much look like that out there. And there's some now disturbing science, and I'll mention this, that suggests that the precipitation declines we're seeing are human caused. This isn't just natural climate variability, that we humans have actually changed the precipitation patterns and amounts in the Colorado River Basin. What about temperature? Same kind of graph. Temperature's up 3 Fahrenheit, 1.7 Celsius since 1970. And importantly, not a single year after 2000 is below the 20th century average. And I would posit to you that we will not ever see in our lifetimes another year that's below that 20th century average. So how can a really good snowpack year like a decent snowpack year like 85% of normal on April 1, when we measure snowpack typically about the maximum April 1, how can it turn into 30% runoff? And this image here is what's called the snow water equivalent, the amount of water that's in our snowpack. You can see it build from October on the left side all the way to a peak around 4/1. And here in 2021, we had 13 inches of snow water equivalent. And this is the year I'm talking about, where we had 85% of snowpack and we got 30% of runoff. We used to think in the 20th century in the Colorado River, the only thing that mattered was this like October through April or October through May precipitation. We knew it rained, of course, in the summertime, but it didn't really affect the river flows very much. I mean, maybe they bounce up a little bit. But that October to April or May runoff all occurs, that October to May snow accumulation then runs off in May, June, and July, April, May, June, July. And so huge, about 75% of the annual runoff occurs in those 4 months. And we used to just kind of discount that summer precip. Oh, it doesn't really matter, it doesn't do anything. If you look at the precipitation in the upper Colorado River Basin, it falls evenly every month. Only June's down a little bit. It's about 1 inch a month over the whole upper basin, much higher in the snowmelt areas. Since 2000, what's happened to our precipitation declines? So a small decline in October through February, large declines here in the spring, March and April, and then in that summer period, June, July, and August. And if you think back, this sort of meets the mass balance requirement, right, of really like 2018 being that crummy year. You actually, or 2021, let's talk 2021 because that's what I'm dealing with here. Pretty good winter precip, but then horrible summer, late spring and summer precip. What happens here? So March and April precipitation declines allow early runoff and early green up. It gets sunny and nice. Snow starts to melt off. It melts off early. The June, July, and August declines, plus these really high temperatures, dry out soils basin-wide. You know, we always focus on human reservoirs, you know, Powell and Meade and Dillon, but nobody realizes that the most important reservoir for life out there is soil moisture. If you're a gardener, man, soil moisture is everything. If you're an ag producer, it's everything. And vast quantities of water are held in that soil. And what we're finding out, here's soil moisture. And this is like July of 2020. So a year before the runoff occurred, the previous summer, you know, the dry summer in 2020, you get the winter snowpack on top of these dry soils that then go to melt in the spring of 2021. Where do they go? They go to replenishing this diminished soil moisture. They don't run off overland until that soil moisture buffer gets refilled. And so, I mean, this is exactly what I'm saying. Previous year, dry and hot summers, along with early springs, sharply reduced runoff, and dry soil serves as this memory that lasts from one year to the next. And our climate system's full of these memories. We don't really appreciate how much they are, and they exist on short-term basis and long-term basis. A quick one that's kind of fun is in the Front Range here in the wintertime, when it snows and you've got this white reflective surface, it's about 20 Fahrenheit colder than when that snow melts. You got this nice brown surface that can then absorb solar radiation. If you check this coming winter, so this is this short-term little memory that's kind of yet one more example. And so the lesson here is that summer precipitation is important. Why? Because it keeps that soil moisture buffer from being too severely depleted for the following year when you need it to ensure you get good runoff. And yeah.
I'm sorry, I have a quick question.
Yeah, and I'll repeat it.
So when that precipitation infiltrates into the soil and replenishes that dry soil, does the basin get any use out of that, or does it mainly evaporate out?
So, I mean, I would argue it's really important for keeping fires down, which is a use that we all appreciate around here. I mean, who didn't like this summer relative to some of the earlier summers we've had, 2018, 2020, 2021? I mean, it's just good all around. It keeps these stream flows higher, so you have fewer harmful algal blooms. The critters that live in the water actually have more water, so they're happier. I mean, there's a lot of good benefits to that soil moisture. It's not just a loss. It isn't just evaporating. Yeah, and excuse me?
Does a lot of it evaporate out of the soil?
So ultimately it does. Soil moisture, ultimately, a lot of it gets ET'd, evapotranspirated away. And I mean, if you look at a mass balance of the whole system, and this is true in most arid systems, about 80% of what falls out of the sky actually goes and evaporates back up, either evaporation from water bodies or streams, or more importantly, and more commonly from plants. That's where the transpiration comes in. And this is a good thing. It's not a bad thing. It's just part of how the water cycle works.
Any other questions? Feel free.
So would you disagree with the mega drought sort of characterization of the Colorado river system?
Yeah, well, let me get to that in a slide or two, and I'm barreling up on my time, but I'll answer what mega drought, how a mega drought ties into this. Yes.
In terms of evapotranspiration, would they have less evaporation if the Powell wasn't in the middle of the desert, or
So
were there other considerations when they were building that?
in terms of evapotranspiration, how does Lake Powell factor in? So both Powell and Meade evaporate, depending on how full they are, maybe 400,000 to 600,000 acre feet per year. A lot of water, but in the scheme of things, it's not huge. You prefer it didn't, but that's just part of the way the world works. In some places, they've tried to cut down on reservoir evap with ping pong balls and other kinds of things that aren't that much appreciated by people who want to use the lake. So yeah, this image just shows early runoff, and I'm not going to spend it 2 to 6 weeks early runoff since the year 2000. I'm going to skip this in the interest of time because it really just duplicates what I've gone through. Why we're losing water, both high temperatures, which cause more evapotranspiration over a longer period of the year, plus the decline in precipitation. So let me wander through some of these studies and I'll get to the mega drought. So really quickly, here's a 2021 story on snowpack, a low to no snow futures, impacts on water resources in Western United States. These folks just talk about how we're going to see a lot more rain and a lot less snow, even in places like the Rocky Mountains, which are far better situated than California and the Pacific Northwest, where they're going to see a lot of their snowpack disappear because right now it's close already to 32 Fahrenheit. And that means in the winter, it'll rain instead of snow. Groundwater, this is a study on how will base flow respond, the lowest component of flow. Again, these folks show these large declines in the upper Colorado River Basin as this entry proceeds. This paper is probably the most disturbing, done by a NOAA scientist down in Boulder and a bunch of University of Colorado scientists. And basically, What they say is the century-long decline in Colorado River flow is tied to these precipitation declines, and those precipitation declines are human caused, which is really spooky. Nobody's actually duplicated this. It's a 2019 paper. This paper actually really makes me very nervous. This study in Science, Colorado River flow dwindles as warming-driven loss of reflective snow energizes evaporation, suggests that for every degree Celsius increase in temperature, you lose 9% of the flow of the river. There are a bunch of different numbers. Different scientists have come up with somewhere roughly 5 to 10%, let's call it that. And because I told you earlier, we've seen 1.7 Celsius temperature rise, do the math. 9% times 1.7, what's it get you? 15% roughly decline in flow since about the 1970s. That's what they would tell you. All right, here's a study, large contribution from anthropogenic warming to emerging North American megadrought, the megadrought question. Park Williams study here, there's a follow-on study. These guys reconstructed soil moisture, June, July, August soil moisture back 1,200 years and found over a large portion of the American Southwest, this is the worst period going back 1,200 years. This particular study in 2020 is the second worst, but then they had a new version of it that came out that I don't have in my slide that calls it the first worst. So this study, increasing influence of air temperature in upper Colorado River stream flow in 2016, gets to this connection between how warmer temperatures cause more evaporation, and so less water is left to run off into our rivers and creeks. And they particularly note in 1988, this kind of started, that's where they detect the trend. And then there are 4 different papers that suggest that up to half of the loss of flow is due to humans. And that's both due to warming temperatures and these precipitation declines. And these are 2 papers I was involved in, and I'm running short on time. So here's Lake Powell near Wahweap Marina. You can see Page off in the distance. That's that vertical arrow there on the upper right. You can see the backside of Glen Canyon Dam if you look carefully. Not too long ago, this little S curve here didn't even exist in the reservoir. And the blue line in the foreground, there's a high water mark in the year 2000. This isn't a drought, it's aridification. And this was just a little piece that I wrote with a co-author that described what aridification is all about in 2020. And I walked you through this early. It's not a drought. It's not the cutesy new normal. Declining snowpacks, earlier runoff, shorter winter, more rain, less snow, higher temperatures, drying soils, severe fires, mortality of our forests. Really important point. As it warms, the atmosphere wants to hold more moisture, 7% per degree Celsius. This is what's behind both bigger droughts and bigger floods. As the atmosphere warms, it's a bigger sponge above our head, it absorbs more, and then when it decides to precipitate it out, there's more there to come out, like is happening right now in Pakistan, right, or happened over the last week, where, according to some reports, 30 million people have been displaced. Really important point. 7% per degree Celsius. Storm tracks moving northwards in megadrought. So hopefully I got you at least a smidge on your megadrought. Megadroughts are droughts that last decades or longer, and they're a phenomenon that around the year 2000 we began to appreciate, and you need these paleoclimate studies to be able to pick them out. Jennifer, I'm running up against time constraints here, right? Okay. So there's a whole bunch of really grim projections. These are out of reclamation on reservoirs and power and upper basin water delivery. We think could go elevation 1020, which is we don't have any rules how to operate the reservoir, greater than 40% chance starting in 2023. Powell at or below elevation 3525. The problem here is we run the risk of being able to generate power at Powell, greater than 40% every year for the next 5. Again, to this section 3D in the compact, I talked to you about these unregulated inflows into Lake Powell and how they're lower than they need to be to meet that. The problem here is we don't know what that means. And there's a whole series of things in the compact that are kind of like this, I got to tell you. And we could violate the longstanding interpretation of that by 2025 and 2026. And these are all not independent, they're all linked. Here's just some flow projections for the 21st century. So my co-author and I suggested we could lose 30% of flow by mid-century. Some other people suggested somewhere between +5 and -40. The climate models do suggest that it could get wetter. I'm really disinclined to believe them based on what we've seen. This report on the right suggested a strong tendency towards lower runoff, upper basin temperatures. This current trend has another 2 Fahrenheit or another degree Celsius by 2050. The models say more than double that's possible. This is just a little article op-ed that I wrote with a co-author in Science talking about how we should manage our risk. And we basically just say, hey, every trend's in the wrong direction. Climate system's non-stationary. You'll hear this term, non-stationary, meaning it's moving. It's changing. Tipping point probabilities are too high. All these bad things potentially exist. We only control our demands. Therefore, to avoid what we call water management malpractice, we got to anticipate the flow is going to go lower than what it has over the last 22 years. How much less? Hard to guess. This is where the decision makers really need to step up and figure out what they want to plan for. But planning for 12.3 million acre feet is not nearly enough. And I'm going to suggest that, since 2000, we've had a bunch of really good incrementalist approaches. And we're now at the point with 2 to 4 million acre feet and reductions needed. That isn't going to get us where we need to go. We really need to think about sort of bigger ideas. Delph Carpenter was the genius that decided in 1922 we could base a compact on the compact clause in the US Constitution, and sort of revered here in Colorado. So I ask, where are our new Delph and Delphina carpenters to help us out of this? So with that, I think I'll end. That's a whirlwind tour. Thank you.
During your period you just went over, have you ever considered using silver iodide to help reduce rainfall?
Okay, so if we ever considered using silver iodide to increase precipitation, absolutely. There are snowmaking programs underway in many of the upper basin states. It's actually a really cheap way to potentially generate runoff. And it seems like there's some science that's supportive that it can. It cannot work if there's no moisture in the atmosphere. It can't work in the middle of a drought. So you got to use it all the time. And it is being used. State of Colorado actually has a well-funded program. State of Wyoming does as well. I'm not so sure about New Mexico and Utah, but I wouldn't be surprised.
Actually, California and Arizona and Nevada also contribute money to those programs.
Other questions? Yes.
By removing water from the basin, do you also, in doing so, remove water from the atmosphere in that area?
So by removing water from the basin, you also remove water from the atmosphere. Yeah, arguably in a mass balance sense. But I think what you're saying is, if we're seeing less precipitation, does that mean we're seeing less atmospheric water vapor as a result of ET, right? I mean, the two are linked. If you got less coming out of the sky, there's less that can go back into it. So yeah, and that gets into this notion of aridification, right? This warming and drying that we're seeing. And the drying can be drying of the atmosphere, not just drying of soils and other things we typically think of that dry.
This is sort of a broad question, but like, what happens if we run out of water?
What happens if we run out of water? So that's what people are grappling with right now, with the 2 to 4 million acre feet. And, I would tell you, so I coined a phrase a while back, 19th century water law collides with 20th century infrastructure and 21st century climate change and population growth. What happens? It's pretty clear to me that, so for example, in the case of the Central Arizona Project, where I come down is Phoenix and Tucson need multiple sources of water. I mean, these huge metropolitan areas have got to have reliable sources of water. And if we've seen anything post-forest fire, communities that have one source of water are really at risk. And there are now multiple cases of this where, I mean, you're out of luck. In fact, this town was out of luck in 2012 in the High Park fire when the Poudre River, ran black. And thankfully, Fort Collins has Colorado River supplies and Horsetooth Reservoir that they were able to then tap into for a number of months. I think we're going to figure out what our real priorities are here. And those priorities are going to contrast a little bit and compete a little bit with prior appropriation and 19th century water law here, where oftentimes ag is the senior water right. I just don't know how you can let, for example, in the case of Arizona, Yuma area farmers, which do really important winter farming for produce that we all like to eat, but how they can utilize their senior right that cuts off, for example, a really important source of water for Phoenix. But that remains to be resolved, how we solve this. The Australians had a really severe drought from 2000 to 2010. And they had an opportunity to look at their water system, and they came up with 3 priorities. First one, critical human water needs. What's that mean? Kind of, what's the water to keep your cities running at, 50% of normal consumption or something like that. They then set the environment, which is not necessarily what would happen here in the US. And then they said all other uses. That was their priorities. I think we too are going to find that there's a critical human water need for Las Vegas as well, which doesn't have a present perfected right, which is a right that predates 1922, which is immune from being cut off. Las Vegas has 2 million people. 90% of their water comes from the Colorado River. How can you possibly think that somehow they wouldn't get water if things got really bad? So I don't know. This is like open season for new ideas and open season for lots of controversy too.
That's Fort Lewis.
Fort Lewis, questions?
I think we're good over here for right now. Thanks for checking.
Great, thank you, Katie. Brad's here. Want to ask some individual questions? I'm sure he'll stick around a little bit.
Yeah, I have a question. Agriculture, the ways crops are irrigated, is that?
Grazed crops. So this is a real issue that's come up. We have lots and lots of forage crops in the Colorado River Basin. So on the upper basin, you'll see a lot of hay, a lot of alfalfa. Alfalfa is a remarkably adaptable crop. Same thing in the lower basin, actually. They grow a lot of alfalfa, depending on who you talk to. Forage crops might be 40 or 50% of water consumption in the basin. It's huge. Brian Richter has a paper on this. It's worth a read if you really want to deep dive. And the question is, do those crops really make sense when push comes to shove? And farmers don't like to be told what to grow. They're very clear about that. But it's an interesting societal question. What's an appropriate crop, and do we have a right to tell farmers what to grow and not to grow?
Let's thank Brad again. We have some individual questions.
If for any reason you want to get a hold of me, please do. I love to be a resource to students who are trying to figure out what to do in the world. Water is a big deal. Climate change is water change. Climate change is water change. Every assessment of climate change I've ever written has an executive summary. And bullet 3 is always climate is water change. Expect more floods, more droughts. And we're seeing that worldwide right now. So